So let's do some examples. So the identity operator is a pretty important operator. Okay, so let's call this I, or 1 hat. So if we have some basis, what the identity operator does is that it takes every vector to itself, right? So in the finite dimensional case, the identity operator in this basis is characterized by the Kronecker delta function, right? So in the infinite dimensional, or the Fourier analysis version, so I should say infinite dimensional and continuous version, what we will have is that if we have E of k, where E of k is one of these basis functions, then the identity operator acting on E of k prime, of course, will just give me E of k prime. And this we know is just delta of k minus k prime. So the Dirac delta function, delta function is simply an operator, is simply the identity operator in the, say, EK basis, okay? So just as, we have these basis functions, EK, which are 1 over square root of 2 pi h bar e to the power I k dot x, there's a conjugate, these are x, right? These depend on x. There are conjugate bases, so these are, in which we can say as E of x of k, right? And those would be 2 pi h bar e to the power minus I kx, right? Because these are just going to be the Fourier transform of the basis of these guys, okay? So we can, talk about these in terms of these bases or these bases. But is it clear how the Dirac delta function is just the generalization of the Kronecker delta? You already knew that, but I'm just trying to formalize these things.
Yes, sir.
Okay. So let's look at more operators. So we saw the position operator. So for example, we saw that the average value, average position of a particle was given by expectation value of x, and this was given by psi of x of psi, right? So so let's look at this. So what is this thing? This thing is psi x of psi is d of x. I'm just 1 second.
He will be Schrodinger's cat now.
Sorry? Schrodinger's cat. Yeah, Schrodinger cat wants to be both inside and outside. He's very annoying. Yeah. Anyway. So, so what is this? This is psi star, which is a function of x and t, and the number x and psi of x and t. Okay? Now, the finite dimensional version of this would be x would be replaced by some matrix, right? Say x, big X is some matrix. And size would be replaced by some, some column matrix. Let's call it psi, and psi, dagger, right? So if I write it out, so this is a number, right? If I write it out in terms of its components, it's going to be ij psi I star. This is just components of this guy. And then this is going to be x of ij and psi of j. Okay, so for the finite dimensional product, we see that we are summing over two indices. But here we seem to be summing over only one index. So what's happening is the following. Let me put this in parentheses. What is happening is that we can write psi of x of psi as this thing. We can change this such that we can introduce another integration, dx prime, such that this is psi star x of t, and then x, and we introduce a delta function, x minus x prime, psi of x prime of t. Now we see that this thing plays the role of this operator. And here we had two sums. Here we have analogously two integrals. Therefore, we can say that the x operator, in the position representation, so we usually denote x by an operator by a caret. If I look at its x, like small x prime elements, so here these are continuous indices. So, here these are discrete indices. Then according to this analogy, this operator is given by the number x times the delta xx minus delta x minus x prime. Right? So just as the identity operator, the xx prime component is just delta of x minus x prime. The position operator, the x operator, its xx prime element is given by that. Okay? So this is also a diagonal operator in this basis. This is also a diagonal operator, right? In this basis. They're essentially diagonal matrices. Is this clear what the analogy between matrices and operators in these two cases?
Yes, sir.
So that was number 2. And let's look at another operator, which was the momentum operator. And we saw that the momentum operator, the expectation value of P, was given by psi h bar by I, the gradient of this, right? We derive this from by postulating that the expectation value of the momentum must be equal to m times d by dt of x, expectation of x. And do you remember that in the derivation I made some mistakes, but in the end we figured it out. So from there, we saw that the momentum operator P is somehow given by h by I d by dx. Okay, so now I want to make it more precise what that means. So let's unpack this. What is this? Psi h bar by I d by dx of psi. This is d of x psi star h bar I d by dx psi of x and t. Let me just make sure that I will actually need the dependent, so I will this is x and t. Okay, so this thing I can think of it as some function phi of a wave function phi xt, right? So then I can do is that I can then insert a delta function just as like before, delta of x minus x prime phi of x prime t, and now I have another integration with respect to x prime. Okay, so so let's write that. We have two integration, one with respect to x, another with x prime. Psi star of x and t, delta of x minus x prime, here h by I, d by dx prime, psi of x prime t dx. So yeah, well, dx prime, I already wrote that. And now what I can do is that I can use the identity of the delta function to bring this derivative over to this guy. Okay. Remember that this thing does not depend on x prime. So this thing is unaffected by this manipulation. So we have dx prime psi star of x of t minus I by h by I, h bar by I, d of dx prime, delta of x minus x prime, bracket ends, psi of x prime of t. Okay? So this means that we can say is our momentum operator in the in the position representation is its xx prime element is given by minus h bar by I, the derivative with respect to x prime of x minus x prime. But remember that we have another identity where we can change this derivative from x prime to x. Writing that, we can also express this as h bar by I, d by dx, delta of x minus x prime, with the minus sign compensating for this change. Okay, so this is a representation of the momentum operator in the position basis, and this is not a diagonal operator. Okay, right? Did you follow this? How P is an operator? How it's an infinite dimensional matrix? Okay. All right, so any comments? Any questions? I'm very happy to stop and discuss this at length.
So could you go up a little bit? The first line. Yeah. So how did where did the phi of x prime t come from? I think I missed it.
Yeah, that's a good question. So this is a derivative operator acting on a wave function, right? So when you take the derivative of a function, you get a different function. So that function I'm just calling as psi. This is the definition of psi.
Psi of x t.
Yeah.
Okay.
Then in the next line, what I'm doing is that I'm introducing a delta function and thereby transforming the x dependence of phi to x prime.
Oh,
Right?
yeah. Okay. I
Okay.
got it now. Yeah.
Okay. Any more questions?